Okay, so I think this is going to be into two different videos, but I guess the purpose of this video and the one that follows, is just to work through the examples of Section 7.1, where it's entitled Basic Integration Techniques, and the idea of basic is obviously a relative term. If you're familiar with these and familiar with lots of different techniques, yeah, these are the ones we've seen so far, and we will get more advanced ones. But some things we forget. And so that's why I want to make a video so that you can hear me explain, go through these. Some you might remember from last semester, some you may not. And so that hopefully we'll have our bases covered, kind of pun intended for the basic, when we move into some more advanced techniques. So feel free to use this video as needed. So if you need to fast forward to an example that you're not sure how to solve, that's fine. And then you could just see all the solutions at the end and check your work. It's up to you. But I like 1a and 1b, kind of together, because notice that natural log of x is in two different positions, and honestly, it doesn't matter where it's at. That almost always becomes your u for u substitution. We don't know how to integrate natural log by itself yet, but it's coming. We'll get integration by parts, and we'll learn how to do that. But anytime you see a natural log, that makes it a good candidate for a u. So here I'm going to let that be my u. And then its derivative is just 1 over x dx. So it becomes a really nice substitution, because remember, this is technically it could be like a 1 over x times ln x. So we can separate that. And again, hopefully that doesn't look, that should look familiar. So then we're just integrating u du, and we have to change our bounds. So if we put 1 in for natural log of 1 is 0. And we put natural log of e, that is 1. So this just becomes u squared over 2 when evaluated from 0 to 1. And so that's just 1/2 minus 0, or 1/2. So hopefully that's okay. Then, in here, the position ln x is in the denominator. That's okay. Right, so we can still let u be ln x. Its derivative is still 1 over x dx, which we see as a placement there, so it works out really nice. So now we're integrating 1 over u du, and then if u equals natural log of x, then e cubed becomes a 3, and e to the 12th power just becomes a 12. But now 1 over u as an antiderivative is the natural log of the absolute value of u when evaluated from 3 to 12. Now, the antiderivative, remember, of 1 over u requires absolute value to match up the domains, but once your values are positive, like 12 is and 3 is, then you don't need that absolute value anymore. It's already done. And most likely you'd see this as the natural log of 4, since you can combine that to be 12, the natural log of 12 divided by 3. Okay, so just 1a, 1b, excellent. Now, the next one, when you have something and it's a rational function, right? And a rational function just means that you've got a polynomial both in the numerator and the denominator. It might not necessarily be just a power rule. It could be natural log, or you might have to do a little work to adjust it in this one, because we need to do long division. Or we can't to be quote unquote simplified in order to actually evaluate integrals, whether it's arctangent or partial fractions. We have to make sure the degree of the numerator is less than the degree of the denominator, which it is not. So I have to do a little bit of long division. So I'm going to divide out x squared plus 6x minus 6, divide that into x squared plus 8x, and I guess that's plus a 0. So x squared goes in x squared just once. So when we get x squared plus 6x minus 6, and here's where I know my honors pre-calc students make an easy mistake. Lots of students, you subtract. So when you bring that down, the x squareds cancel. It's 8 minus 6, so it's a 2, and 0 minus negative 6, so it's plus 6. So this remainder that's left over, I know I can't divide anymore because the x squared is greater now than our remainder. So our problem can be written as an equivalent problem from 1 to 2 of 1 plus 2x plus 6 when divided by x squared plus 6x minus 6. And so I've appropriately simplified this. And again, looking at your degree of your numerator, it's linear. The degree of the denominator is quadratic, so it's one less. And anytime it's one less, check a U substitution. Maybe it's going to work out perfectly, and it actually does. The green highlighted, if I choose that to be my U, yellow above is the du. It's perfect. So this was written for that exact reason. If not, then we'd have to do other techniques like complete the square, or partial fractions, all the fun that comes with integration. So let's go ahead and then solve this. So this portion right here, I'm going to let U be x squared plus 6x minus 6. So its derivative is 2x plus 6. So that's perfect. And so then, if I can sort of separate this. So this is still going to be the integral from 1 to 2 of 1 dx plus, and then I'll have the integral, and I'll change my bounds since I'm just going to integrate 1 over u du. So now my lower bounds, I'm going to fix that. I'll use a different color to highlight. So when x is 1 plus 6 minus 6, so we get a 1 for that bound. And so then 2 squared is 4, and then 4 plus 12 is 16 minus 6, so that should be 10. So then I don't even have to go back, and this integral here can just stay in terms of u. So antiderivative over here, go back to that darker color here. So that's just x when evaluated from 1 to 2. I realize that's a different color, but that's okay. Plus, and this is natural log of the absolute value of u when we evaluate from 1 to 10. So this just becomes 2 minus 1 plus, and then this is natural log of 10 minus natural log of 1. And notice I didn't need the absolute value anymore because those numbers are already positive. Natural log of 1 is 0, 2 minus 1 is 1, so then we get 1 plus the natural log of 10. Okay, now example 3, if you try to do a u substitution, I'm noticing that this is quadratic and this is linear. Remember, if you tried to do this, and this should be sort of like your first line of defense, right? Your first technique, you get negative 2x. So even though I could move this is a negative 1/2 du is equal to x dx, it doesn't account for this extra 3. But if it's just a 3, if it's just something you're adding, the technique here is that we separate it into 2 separate integrals. So I'm going to go ahead and erase this, and I'm going to break this up into a summation, or not a summation, sorry, a sum of 2 integrals. So then, and that's sort of like our next, I guess, our next technique or our next strategy. So it's still going to be integral from 0 to 1. We'll leave x divided by the square root of 4 minus x squared dx plus, and then the integral from 0 to 1 of 3 divided by the square root of 4 minus x squared dx. Now, on the left, this one can be solved through a u substitution. On the right, we need an inverse trig function because it's a difference of squares, and it's a square root, has this, has that structure of arc sine, and that's where we have to kind of be at the point now where we recognize that, a squared minus u squared, that's arc sine. And so if you had Mrs. Moore last semester, she may have taught it or approached it a little bit differently, but in result you'll still get the same antiderivative. So what I'll do is I'll kind of come over here. So then for this one, I'm going to let u be 4 minus x squared because its derivative is negative 2x dx. And now I know that I could just, like I had written before, negative 1/2 of du is equal to x dx. So for that portion, the bounds will change. So instead of going from 0 to 1, they'll go from 4 to 3, which is fine. Right, because when x is 0, we get 4, and when x is 1, we get 3. So we go from 4 to 3, and then it's just going to be negative 1/2, and that's 1 over the square root of u du. Plus, now for the second integral, maybe I'll switch to purple here. So I'm going to let, I know that it's perfect, like if u is just x, So du is dx, so that's fine. And my a value could be 2, because 2 squared is 4. So that really it's actually perfect. I know I've got a 3 up there that I'll put in, but it can still go from 0 to 1 of 3 over the square root of 2 squared minus u squared du. That, again, that's that characteristic structure of arc sine. So then we'd sum those up together. So then guys, go back to red. So this antiderivative, remember, u as a square root in the denominator, that's u to the negative 1/2 power. So when I bump it up a power and divide by that power, so u to the positive half divided by positive half. So you have negative 1/2 coefficient, u to the positive half divided by half, which is nice. That'll cancel, which from 4 to 3 plus, and then this one here is our arc sine. So don't forget the 3. Now it's not 3 over a. It's not 1 over a. That's only arctan and arc secant. So it's just 3, but then it's arc sine of u over a. So u over 2 when evaluated from 0 to 1. Okay, so then we can simplify that. So then the 1/2s cancel here. I guess I should have changed colors, but that's okay. I'll go to this green color. So then that's just negative the square root of u when evaluated from 4 to 3 plus 3 arc sine of 1/2 minus 3 arc sine of 0. Arc sine of 0 I know is 0. Arc sine of 1/2, remember, it's the principal root, so that's pi over 6, or a 30-degree angle, but we think radians times that 3. And then this is just negative root 3 minus negative root 4. So we just get a whole eclectic set of kinds of like numbers, right? We've got square roots, we got pi, we've got an integer, so we end up getting negative root 3 plus 2. And then plus pi over 2, which is kind of a interesting value, but that's what it is. Okay, so let's do maybe just one more example on this video, and then I'll let you you take a break or go to the next video for the other solutions, because this one, again, you might think, ooh, I have maybe a completing the square issue here, but go back to that very first, right? Go back to that very first strategy. Could that be your u? Could u equal 10x minus x squared? If not, maybe we have to break it up or try to complete the square. But in this case, I think we're good, right? Du is equal to 10 minus 2x dx. That's just off by a factor of 4. So 4 du's are equal to 40 minus 8x dx. And so that's right there, right? So I can rewrite this then with a u substitution. So it's the integral of 4 over square root of u du. Let's fix our bounds. When x is 1, we should get 9 as my lower bound, right? 10 minus 1, so it becomes 9. When x is 4, we get 40 minus 16, which is 24. Now, we just did this antiderivative. Remember, u to the negative half, we bump it up a power. So we have 4u to the positive half divided by half when evaluated from 9 up to 24. And I like dividing by that 1/2. I put those parentheses there to kind of emphasize that's going to come up as a reciprocal. So it's the 8 square root of u when evaluated from 9 to 24. So that's 8 root 24 minus 8 root 9, in which that's a 3. So that becomes a 24. And there's a perfect square of 4. So a 2 comes out. So we get 16 square root of 6 minus 24. Okay. Now, just a little preview, right? For the next one, notice the only difference. Instead of 40 minus 8x, we did just a 40. So obviously a u substitution is not going to work. And again, just a reminder that we didn't have to separate the 40 and the 8x into 2 separate integrals because the u substitution was perfect. Where the previous example, number 3, we did, because we didn't have that direct u substitution. Okay, so like I said, I'm going to follow up with a second video for the last 4B, 5, 6, and 7. And you can use the video to whatever needs you have. Watch it through, listen to the commentary. I'll give you a play-by-play action of the problem, or just go to the end and see all the answers.